if you think about what we've been talking about for the last couple of days with all this acid-base chemistry, then what we've been talking about are chemical reactions where some molecule, which has an H on it, transfers that H as H plus to another molecule. Right? So we can think about acid-base chemistry as being like proton transfer chemistry or proton transfer reactions. And we call the thing from which the proton is transferred the acid, and the thing to which the proton is transferred the base. What we're going to do now is we're going to look at similar sorts of chemistry, except rather than transferring a proton, rather than transferring an H plus from one thing to another, we're going to be transferring an electron from one thing to another. Right? So it's the same sort of idea, but as we'll see, when it comes to these electron transfer reactions, we tend to look at the reactions themselves in a bit more detail. And then what I need to do, it just occurs to me, is find you another YouTube video.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
In the good old days, we could have done this in here, but not anymore. Right, there it is. How exciting. So, the point was, so that shows you what the reaction is like. You start with chlorine gas, which is the green gas in the flask, and you start with a little piece of sodium metal, and you do this reaction. All that white stuff that you made is sodium chloride, right? That's just salt, all coating the walls of that flask. So we can summarize that reaction like this. We start with sodium metal, and we start with chlorine gas, and we make sodium chloride, an ionic compound, which is just salt, which is a white solid. Yeah? And see, if we write an overall reaction like that, if we compare that, again, as I'm trying to suggest we can, with the acid-base chemistry, then in the acid-base chemistry, you can see, just from the overall equation, the H that's transferring from one molecule to another. Right? It's going from the acetic acid to the water molecule. And you can see that here. But for an electron transfer reaction, it's not so clear. You can't see in the overall equation how the electrons are moving around. And so what we do to try and see more clearly how the electrons move is we take this equation and we pull it apart. Okay? Because sodium chloride's an ionic solid, we think about sodium chloride being composed of sodium cations and chloride anions. Yeah? We did this right back on the first day last week. And so what that means is that in our chemical reaction, the sodium metal, which is just sodium atoms, are turning into sodium cations. So the Na solid is turning into Na plus. And to do this, the sodium atoms must be losing one electron. Right? Remember, they can't gain a proton to become positive because then they would turn into magnesium. They have to lose one electron, and then you have more protons in the nucleus than you have electrons going around the outside. And so overall, the thing has a positive charge. Yeah? And so we can write a little equation to describe just this bit of the reaction that we've done. And we can write it like this. We can write Na as a solid, so that means sodium atoms, goes to Na plus, sodium cations, plus one electron. Right? So in the course of this reaction, we start with sodium atoms, we make sodium cations, so that means we must also make one electron. If you like, the reaction involves the sodium atom falling into two pieces, a sodium cation and an electron. Yeah? And so we symbolize electron just with a little E with a negative charge on it. If we then think about the chlorine gas starts off as Cl2 molecules, and we can think about that as just being two chlorine atoms stuck together with a single covalent bond of the style that we saw in the lecture the other day, right? So there's no Cl plus and Cl minus or anything, it's just two chlorine atoms stuck together, sharing an electron with each other to make a molecule. If we take that and we look at what that goes to in our chemical reaction, we can see that the chlorine gas turns into chloride ions, Cl minus. To do that, the chlorine atoms in our molecule must each gain an electron. So they start off being neutral, they end up being negatively charged. They do that by getting an electron, so they've got one more electron around the outside, then they have protons in the middle, so overall the thing has a negative charge. And so we can write a little equation to describe that part as well, and it would look like that. Now we've got some balancing in there because it starts off as Cl2, but Cl2 gas plus 2 electrons gives 2 lots of Cl minus anions. Okay, we happy with this? So if we take our overall equation and we break it into two parts, so this way we can see a bit more clearly what's happening with the electrons. The sodium atoms are turning into sodium cations, so that means that in our reaction the sodium atoms must be losing one electron each. The chlorine molecules are turning into chloride anions, so in the reaction each of the chlorine atoms must be getting an electron from somewhere to give them an overall negative charge. And it turns out we have names for each of these types of reactions. I should apologize ahead of time. If you start getting worried about how I spell the word lose, it's because I've never known how to spell the word lose. So if it's wrong somewhere, then just bear with me. I never know. Has it got one O or two? One O. It's got, so that's right? So it was wrong the other day somewhere. Yeah, okay, cool. I never know. This is science, not English. We call a reaction in which a molecule loses an electron, or possibly more than one electron, as we'll see. We call that reaction an oxidation. And if we have a reaction in which a molecule or an atom gains an electron or electrons, then that little reaction is called a reduction. And so this is important, and so people have come up with ways to help you remember this. I like lions. Some people have oil rigs. Who had oil rigs at school? See, boring teachers. I like lions. Leo goes grr, yeah? Loss of electrons is oxidation. Gain of electrons is reduction. Leo goes grr. If you know about oil rigs, that's fine. Remember oil rigs. But either way, you need to know that if you have a little reaction where something loses an electron, that means that the electron is a product in that little reaction, then that's an oxidation. Whereas if you have a reaction where something gains an electron, so the electron is a reactant, then that's a reduction. Okay, so that means that we can say that this little equation here is an oxidation. Na solid goes to Na plus an electron. We would call that an oxidation. And the reaction in which the chlorine gas gains electrons to make chloride anions would be an example of a reduction. So when the reaction happens, like we saw in the little movie, where you have your piece of sodium in your flask of chlorine gas, when that reaction happens, it's important to realize that the electrons that are gained by the chlorine are obviously the electrons that are lost by the sodium, right? The sodium doesn't lose electrons and the electrons just sit somewhere out and somewhere, and then the chlorine gets some electrons from somewhere else. The same electrons that are lost by the sodiums are the ones that are gained by the chlorines. And so the electrons are transferred from the sodiums to the chlorines. The process by which that transfer happens is not straightforward and is not something that we're going to get into at all this year, really, not only bridging, but even in 191. We do a little bit in 191, but not really, because it can be very, very complicated. Even what you would think would be the most simple electron transfer reactions can in fact be years of work trying to work out how they happen. But the important thing to know is that the electrons do not exist out in the solution somewhere by themselves. The transfer is directly from the sodium to the chlorine in this case, somehow. Right? There used to be an ad on TV with these little kids that looked like marshmallows. It was a water safety ad and said, never swim alone. Yeah? So it's like electrons. Electrons never swim alone. They don't exist in the solution. They always get transferred directly, somehow, from one molecule to another. Right? So we write these little equations, but these little re-equations don't exist in isolation. Yeah? And so because they don't exist in isolation, then even though we write these two little equations, what we call half equations, they are always halves of an overall equation. And so here's here's our little oxidation equation, here's the little reduction equation, and what we can do then, once we've got these, is we can combine these back together to get an overall equation to describe the electron transfer reaction. When we do this, though, we have to realize that because the electrons that the chlorine is gaining to turn into chlorides are the electrons that the sodiums are losing, then the number of electrons being lost in the top equation has to be the same as the number of electrons being gained in the second equation. Yeah? So when we come to combine these together, we have to multiply that first equation through by 2. So in other words, each time a Cl2 molecule is reduced to 2 chloride anions, 2 atoms of sodium have to be oxidized. Yeah? The first equation has to happen twice for each time that the second equation happens once. Does that make sense? Hello? Because the second equation requires 2 electrons, and the electrons can only come from the sodiums losing them. So if each time a chlorine turns into chloride, it needs 2 electrons, that means that 2 sodiums have to have lost their electrons to provide those 2 electrons for the second one. Yeah? We happy? So then we can write them like that. And we can add them up in the way that we've already seen a bunch of times now for adding equations together to get an overall equation like that. And then if we've done it correctly, what you should find is that the number of electrons on the left-hand side of the arrow in the overall equation should be the same as the number of electrons on the right-hand side of the arrow. And so then we can cancel those out. And we end up with our overall equation, which is what we started with. Right? And so this overall reaction is what you get when you add together the reduction equation and the oxidation equation, and so overall is called a redox reaction, an electron transfer reaction, or normally just called a redox reaction because it's a combination of a reduction and an oxidation. And you could probably make a case to say that redox reactions are the most important types of reactions that there are. There's really only 3 types of chemical reaction. There's acid-base, there's redox, and then there's something called metathesis, which is kind of like precipitation reactions. Yeah? And of those 3, redox is probably far and away the most important. Obviously, well, maybe not obviously, but photosynthesis fundamentally is a whole series of redox reactions. And so the way by which the sunlight is transferred into energy in plants, which is transferred into energy in people, is all due to redox reactions. And you could argue that, in fact, the start of society as we know it was due to redox reactions, because you could argue that the first great sort of step forward in terms of technology that led to society was people working out that you could take rocks and you could take burnt sticks and you could heat them up in a fire and you could make metal out of them, right? Initially, you know, Bronze Age and Iron Age and all that sort of stuff. All of that reaction of a rock plus a burnt stick to give metal, that's a redox reaction. Yeah? So redox reactions are everywhere. They're very, very important. We're going to talk a wee bit in 191 about how redox reactions are important in biology. We're going to talk a little bit about photosynthesis, talk a little bit about something called ATP. Has anyone heard of ATP? Yeah? And the way that ATP is made is due to a whole series of redox reactions. Very, very cool stuff. This is all the stuff I teach in 191, so I should calm down. But it's very cool. Yeah? So we'll get to do a lot of this. Okay, so more definitions. The only thing about the redox chemistry is that it's full of definitions. And you have to get your head around them, which means that I have to make sure I've got my head around them teaching you, which is why I've already had 3 coffees this morning. I don't know whether it's helping or not, but nonetheless. We can think about the sodium as the thing which causes the chlorine gas to gain electrons in our reaction, because the chlorine gas couldn't gain electrons unless the sodium provided them. Yeah? So if you like, the sodium atoms are the things which enable the chlorine molecules to be reduced. And so we can call the sodium atoms the reducing agent or the reductant. Okay? Reducing agent tends to be the more high school word. Reductant is the word you're going to see here a lot more. Right? But they mean the same thing. So the sodium is the reductant because it is the thing that enables the chlorine gas to be reduced by providing the electrons. Okay? So if you like, the reductant is the thing which itself is oxidized. And then we can say the same thing about the chlorine. We can think about the chlorine as the thing which causes the sodium atoms to be oxidized, because you can think about the chlorine as the thing which takes the electrons off the sodium to get them for itself. And so we can say that the chlorine gas here is the oxidant or the oxidizing agent, the thing which causes the sodium atoms to be oxidized. Okay, we happy with that? Oxidants and reductants. You need to be very, very familiar with those words, especially oxidant. The oxidant is the thing which, see, be careful now. The oxidant is the thing which gets the electrons. The oxidant is the thing which is itself reduced. Yeah? We're going to use that word a lot over the next couple of days and later in the year. Okay. Let's have a look at another one. This is maybe one that you've done somewhere. If you take a solution of copper 2 plus ions, which would be a blue solution, and you put into that blue solution of copper 2 plus ions a piece of zinc metal, then what happens is that the blue color of the solution slowly goes away and the solution becomes colorless, and the piece of zinc metal gets this sort of this orangey brown fluffy stuff growing all on the outside of it. Yeah? And if you were then to go in and analyze your solution and the fluffy stuff afterwards, you find that in fact the solution now contains zinc 2 plus ions rather than copper 2 plus ions. And the fluffy stuff is actually solid copper metal. And so the reaction is copper 2 plus ions plus zinc gives copper and zinc 2 plus ions. Now the sort of thing that we want you to be able to do is if we give you an equation like this, is we'll say work out what the half equations are, write out balanced half equations for the oxidation and reduction processes that are going on here, and then use those to combine them back together to get the overall equation. Right? With this one, that's not too bad, but we're going to see some curlier ones later on. Yeah? But that's generally the sort of thing we need you to be able to do. So if we're going to write out the two component half reactions here, then the first thing we have to do is work out which reactant goes with which product. And here, hopefully, that's pretty obvious. There's going to be the copper 2 plus going to copper, and the zinc going to zinc 2 plus. Yeah? You can't have copper 2 plus turning into zinc 2 plus. That's physics, yeah? Not chemistry. So here's going to be one of them. Copper 2 plus turning into copper. For copper 2 plus ions to turn into copper atoms, the 2 plus charge has to be neutralized, and so we do that by adding electrons to the cation. So copper 2 plus 2 electrons gives copper metal, copper atoms. Yeah? We're happy with that? Would this be an oxidation or a reduction? Who says oxidation? Who says reduction? More people say reduction. Who says oxidation? Oh, still one brave soul. This is a reduction. Because it's gaining electrons. Leo goes grr. Gain of electrons is reduction. The other half equation will be the one for the zinc. The zinc will go to zinc 2 plus, and so for zinc, which starts off being in its neutral atoms, to go to zinc 2 plus cations, it must be losing 2 electrons. And so we can write zinc solid goes to zinc 2 plus 2 electrons, and this one, because the zinc's losing electrons to make the product, will be called the oxidation. Okay, so we can take this overall equation and split it into two halves like this, a reduction half equation, an oxidation half equation. In our reduction half equation, the copper 2 plus is going to be the oxidant, because it's the thing that causes the other thing to lose electrons. If you like, in this reaction, the copper 2 plus is taking electrons off the zinc. So the zinc loses electrons and turns into zinc 2 plus, and the copper gets those electrons, the copper 2 plus gets those electrons and turns into copper. So the copper 2 plus would be called the oxidant, and so the reductant is going to be the zinc, the thing which enables the copper 2 plus to gain electrons and so be reduced by providing those electrons to it. Oh, and there you go. And so I've already been saying this, but we would call that first one the reduction half equation and the second one the oxidation half equation. They're called half equations because we can put them back together to get a whole equation, which is the one at the top. Yeah.